Swayam Prabha. Digital India. Educated India.
Delighted to be here. So, just to give an intro of myself, I'm an assistant professor at Wake Forest University, which is a private university in North Carolina, United States. And I lead a research group working on quantum nonlinear spectroscopy, which is basically the topic of this course. So, it kind of goes very much hand in hand with what I do for a living, so, or part of my living. So the course kind of is structured at reasonably advanced level, kind of assumes that you have fairly good idea of quantum mechanics, at least 1 and 2. The first 2 classes will go over the basics which are required, if not in detail, at least give you a purview of what is a starting point that you would want to kind of dig deeper as we go along in the course. Note that I'm also an experimentalist, so I'm very much strongly tied with experiments, not with theory. So the perspective that you are going to project, given also that my course coordinator is also an experimentalist, will be that of an experimentalist perspective. So the idea is, okay, if I look at an experimental data, how am I going to build a story out of it? That is one part of it. The second part of it, let's say I have an unknown and an unanswered question regarding some part of material physics, and how would I come up with an experiment in order to answer this question effectively. So at the end of the course, I hope you will gain some insights into either of these sort of viewpoints. Again, the course is quantum optical spectroscopy, I think from introduction to state of the art. Now, quantum optical spectroscopy can mean many different things, especially if you just Google quantum optical spectroscopy, many different things come up, particularly use of quantum light and so on and so forth. Now, what are we focusing on here? We are specifically focusing on 2 different aspects. One is what one would call a semi-classical approach, where you treat matter as quantum. There are different energy states. You can have transitions between the various energy states in the material system, possibly, most likely driven by light. But you treat the electromagnetic wave interacting with the medium classically. It's electromagnetic field. Now, if you kind of recall your classical electrodynamics, intermediate level electrodynamics, what you would see is that the Lorentz-Drude model is that you come with an electromagnetic field, you generate a polarization, right? And this polarization will emit radiation. That's what you measure. The electric response function, so on and so forth. And typically in classical electrodynamics, we treat linear. We work in the regime of linear dielectrics, where the polarization is considered proportional to electric field. But you can also write this polarization using higher order responses, something which called a square, cube, so on and so forth. So there is a concept of nonlinear polarization. That is something critical important thing. Electromagnetic field comes, interacts with material, it generates a polarization. The most simplest case is polarization is linear, but it can also be nonlinear. Now, a big link that we are going to make, that nonlinear polarization that you are going to generate in specific resonant conditions is going to have a wealth of information about the material that we are looking at. So we can use this nonlinear polarization to understand what's happening in the material. Now, what do you think will happen in the material? For that, let me first define what our material is. So our material that we are going to work with, given that you are doing optical spectroscopy, okay, spectroscopy means that you are going to use light to kind of see the ghost. It's what So you're going to interrogate. So to be able to interrogate a material with light, it should be responsive to light. I cannot take a transparent material which is not absorbing, which is not doing anything to light, and interrogate that material with light. I may be able to do that in some cases, but mostly it's not. So we are looking at materials which fundamentally interact with light. When I say interact, it will absorb and possibly emit, right? So absorption, emission happen. Now, have you done an absorption measurement ever? Right? You take a material, like if a material looks red, what does it mean? It means it's absorbing the blues and the greens, right? So that's because there are transitions there. There is a particular ground state and there is an excited state. Okay. Nothing happens when I'm coming with possibly red light, low energy light, but as I go more closer to the resonant frequency, I will have a transition, right? And if I measure the spectrum of this absorption coefficient or optical density, it will have a certain spectrum. If I have a single transition like that, it will have a transition that matches with the transition frequency or energy of the energy difference between the ground and excited states, right? Everybody knows this. Now, there is something peculiar about the spectrum I have drawn there, right? It is a particular line shape. Pardon for my horrible artistic skills. It is a Lorentzian function or Gaussian function, right? Doesn't look like that, but there is a line shape associated with it, with some line width. Okay. Does anybody know what this line width of this transition represents? You can answer. You can kind of guess if you want. What do you think this line width? So I have drawn a transition here, a discrete transition. So I would expect to see a delta function here, but it's not a delta function. It has a finite spread. What does this finite spread correspond to? Very good. It's a lifetime. Yeah. Uncertainty. Let's not get into uncertainty aspect of it, but definitely related to finite lifetime. This excited state has a finite lifetime, and the presence of this finite lifetime will manifest as a finite line. Hopefully, by middle of this course, what I just said in plain English will be translated to mathematical formalism. So it's deeply rooted in quantum mechanics, what we call as Kubo-Anderson theory on line shape. So hopefully we will get to that point. That's one aspect of it. Now it so happens that this transition that I draw here is some excitation in a realistic material. And if I take a realistic material, I have some excitation here, but I have a bunch of excitations that are sitting there. They're not sitting in vacuum, they're in real material. They're interacting with everything surrounding them. Okay, what one can define as the bath. So a primary thing as a material physicist is to fundamentally understand and characterize and importantly quantify those system bath interactions. What kind of interactions? So a realistic material is made up of some crystal lattice or a bunch of molecules. And these molecules or the crystal lattice can vibrate, can oscillate. So what we could refer to as phonons. So my photo excitations that are sitting there can interact with these phonons, can have both elastic or inelastic scattering happening. Okay, or these excitations can interact with each other. There can be many body scattering, and this many body scattering can also be elastic, or it can also be inelastic. When I say inelastic, two excitations can come together and form new particles, new quasi-particles, okay, which are two quantum excitations, okay, or it can form repulsive states, so on and so forth. It's kind of multitude of things that can happen, and as a material physicist, I would want to know very precisely what are the mechanisms driving such processes, okay, and also to be able to quantify them rigorously, okay. It so happens the optical line shapes of simple spectra that is drawn there gives you access to that. However, hopefully we'll show in this course that the linear spectrum that are shown here, simple absorption, may lack sensitivity and selectivity to various processes driving those system path interactions. Okay, meaning linear spectroscopy will have severe ambiguities, which will complicate your life. You may not be able to disassociate, for example, interaction of your photoexcitation with vibrations, inhomogeneities in your crystal lattice, or many body interactions, so on and so forth. It may be insufficient. On top of that, at a fundamental level, the physical insight is very limited. Okay, this is where we want to go from this linear regime to a nonlinear response. Okay, nonlinear response, and it so happens those nonlinear response functions fundamentally give you access to a wealth of information which is not accessible to linear spectra. So I'm sure everybody has done linear absorption or seen linear absorption spectra, which are very easy to extract. Same goes with photoluminescence, which is basically you excite and collect the photons emitted by the material. Both of these will have a line shape which looks similar to this. Very, very powerful, no doubt about it, but is highly limiting. Okay, that's a very important thing, because given that it's a very easy methodology to kind of explore, it is widely used by material physicists. But however, there is severe kind of ambiguities in the mechanistic insights that one can draw with this spectrum. That's why we need to go to nonlinear response. So idea is we should be able to relate this to nonlinear response functions, mostly third order, which are related to your third order polarization, fundamentally through the third order susceptibility. Now, if all this looks alien to you, don't worry, we'll go into details of that. So part of this course is to understand or develop the formalism to be able to get a picture of this relationship. Okay. All right. So this is one part of it. So you may ask, where is the quantum optics there? There is no quantum optics here. As I said, light is electromagnetic wave in this case, but quantum mechanics is at the heart of it. And of course, the link that we make between the classical electromagnetic wave and quantum matter is through this magical dipole, transition dipole moment operator, which again is something that we will derive. What is the interaction Hamiltonian driving light matter interaction, which is something that we will derive in this course. But I will also show that, by the way, all these nonlinear response functions, you will access it particularly through ultra-short optical pulses. So there will be part of the course where we will go into experimental methods, which include how to generate the short pulses, how to manipulate these short pulses, how to do the actual measurement to access this. That's also part of the course. But because you're using ultra-short optical pulses, and because of signal-to-noise ratio limits, you are going to bombard the material with extremely high excitation densities. That is the reality. You have to live with. Okay, and you're also going to generate an ensemble of single particle excitations, an ensemble of excitations, and see the response function as an ensemble average. Okay, and also I wrote here as a third order response, and you will see a third order response exclusively accessed through a three field interaction or three pulse interaction. Now again, that's an assumption. There are two problems with it. Nonlinear spectroscopy is fundamentally an ensemble average, and it is assumed to be a third order response. Now both of this have serious questions, because the ensemble average of single particle excitations may not be true, especially if I am coming and hitting with enormously large excitation densities. And also, when I have large excitation densities, there is no reason for me to believe that I'm only the third order, but not in some higher order terms. Okay, there are ambiguities because of that. Hopefully, I will talk about that. And because of that, okay, this is not really a topic which is at a level where I can give instruction directly, because it's a method that we are developing in our group with our collaborators, where we are trying to use quantum light and seeing if we can use single photon level excitation to access the nonlinear response function. The answer for that is we don't know yet, but I would like to give you that perspective and kind of more drive or emphasize the need to think in that direction, to go beyond the standard approaches. Okay, that will be a second part of the course. Okay, all right. There are a few, let's say, details of the course. We'll have some homeworks, I suppose, which we will put up, and we can discuss those homework problems during tutorial sessions, which are closely going to go with the lesson plan. Also note that I'm teaching this for the first time, so we're also developing it, we are figuring it out. So it's kind of a joint work between us and you guys to kind of develop this in a proper way. So the first part, as I said, today and maybe the next class, we'll go over some fundamentals of quantum mechanics relevant for this course. Then I'll give a brief introduction. So by the way, we'll have some simulations using a Python package called Qtip, appended with a package called QDPy. Sounds funny, but it's quantum dynamics toolbox for Python toolbox for quantum dynamics. It's developed by my collaborator Eric Paitner at Houston and several of his colleagues at Los Alamos National Lab. So hopefully we'll get at least an idea of the simulations, which basically calculates the response functions. So I'll also give some introduction to that. But before doing that, I want to dwell and basically go into details of the formalism. And the formalism that we are going to talk about, semi-perturbative expansion of nonlinear response function, is primarily motivated by the work of Shaul Mukamel. Those in the field will know that I should not be recording this, but anyway. There is Shaul Mukamel's book, which I have in my book in my bag. Shaul Mukamel is considered a father of nonlinear spectroscopy, a spectacular array of work for several decades now, which has been used and tested on real experimental system. We use it to explain our experimental data. Sometimes it gets too complicated, especially for experimentalists. So we're going to go to the, for the lack of a better word, dumber version of Shaul Mukamel. And in fact, there are certain notes written by Martin Zani called Mukamel for Dummies. We will use the Mukamel for Dummies. It's not because this class it's good for me as well. I'm at the level of Mukamel for Dummies. I think it's good enough. So that will be our kind of focus, to kind of get the Mukamelia at a very basic response. All right. So today we'll get started. Review of time-dependent quantum mechanics. So that will be a topic now. Of time-dependent quantum mechanics. So we are going to kind of introduce the concept of coherence here, concept of exponential operators, and also a time evolution operator, which is a specific case of exponential operator. And we are going to introduce, the biggest takeaway from this is the concept of time ordering, which is used extensively while treating the solutions for a time-dependent Hamiltonian. So a time-dependent Schrodinger equation. Time-dependent Schrodinger equation, everybody knows this. The Schrodinger picture. Hopefully move from the Schrodinger picture soon. Start with that. Right? Everybody is aware of this. So time evolution of your wave function, of course, is given by this equation, the Schrodinger equation, where h here is time-dependent Hamiltonian. The most general kind of formalism can be written as this. Let's operator. Of course, note that at the end of the day, you're calculating some response. So you are going to calculate expectation value of a given operator. So you have some operator A and expectation value of that operator is given by this. So use the bracket notation. Okay, this is expectation value, and because expectation values must be real because they're associated with physical observable, A must be Hermitian. So now, I think everybody knows this, but anyway, we'll go over it. So we can have a time independent Hamiltonian. If I have a time independent Hamiltonian, then my H will simply be H of R. If I have time dependent Hamiltonian, then it will be H of R comma T. Okay, so that's what we are looking for. And for that, let's say if my time independent Hamiltonian, time independent Schrodinger equation has solutions of the form then the solution for the corresponding time dependent equation can be written I'm not going to show this, it can be derived. So the only time dependence is in the so-called phase factor. And of course, we are assuming phi are the stationary states of the system. More generally, your psi of RT, sum of sums n. Right? Now, for such a system, for such a wave function, what do you think? How does the probability density for such a system behave in time? If I have such a wave function evolution, let's take a simple example. Let's take a two-level system. There are two eigenstates of the system. So I'm able to write psi to be some C1 phi1 e power minus I e1 t over h cross plus C2 phi2 I e2 t over h cross. That is the case. P of t, which is probability, will be psi square. How does that look? Expand, substitute and expand this out, you will see that will be 1 square plus 2 square plus 2 psi 1 psi 2 cosine omega 2 minus omega 1. Omega 1 and omega 2 are the frequencies of each of those states associated with states. Right? Basically, you can see that my probability density is oscillating at the frequency of the difference frequency between the two states. Right? So what I'm having here is a coherent superposition and the probability density is oscillating. Okay? So the state of the system that gives rise to this time dependent oscillation in the probability density is referred to as the coherent superposition state, or simply sometimes, for the sake of convenience, referred to as coherence. Okay? So I can generate a coherent superposition of the state, the probability density will oscillate, and this coherent superposition state is referred to as coherence. Now later on, coherence is going to be at the heart of this course, that's why I'm introducing it up front. Later on, we'll distinguish coherence from what is referred to as the population. So for example, when you're doing a linear absorption measurement, okay, you're looking at the probability of a transition, right? Going from ground to excited state. You're not probing a population in the excited state. What you're probing is this coherence. Okay, using light, you're creating a coherent superposition of a ground and excited states, and that's what you're accessing. It's very important. So fundamentally, absorption, to just do absorption measurement, is a coherent experiment already. It is accessing the coherence. Unlike, for example, photoluminescence. You shine light, you absorb, and then the sample emits. That's an incoherent experiment. An absorption is a coherent experiment, quantum mechanically speaking. Okay? I want you to think about this, come back to me with more questions. But that's a very important point. By the way, this time oscillating form can also have an additional time dependent phase factor, which I have not written out, that can arise from complex expansion coefficients, which has some important significance later on. So the real and imaginary part of the response functions can have a finite phase associated with them, where the many-body interactions have information encoded in them, which is something that we'll treat later. Okay, clear so far? Just a review of time-dependent Schrodinger equation. We have not solved it. We're just kind of putting things out there. Okay, the next section, I'm going to introduce section, call it 1.2. Here I'm going to introduce what are called exponential operators, which have this form, where A is an operator associated with a physical observable, then I can write an exponential operator of this form. Basically, what do they do? What are the exponential operators used for? Is that they act on wave function to move the wave function either in space or time or both. Okay, that's the advantage, that's the utility of exponential operators. For example, if I want to evolve a wave function in time, then my time evolution operator, usually represented by u, is e power minus I h t over h cross. When I operate this on a wave function, I will propagate my wave function in time. Okay. Some properties of exponential operators, I mean, again, for the sake of completeness, I'm just stating it. First properties is that since A is Hermitian, why is A Hermitian? To get the real values. get real values for the physical observable, right? You can show that T must be unitary, which means inverse. So basically, Hermitian conjugate of T basically reverses the action of T. It has to be literary transformation. The second thing is basically if A phi n some A and phi n, and if A phi n and psi n, which means eigenstates of A are also eigenstates of T. Eigenvalues of T are some functions of eigenvalues of A. These are two important properties that is worth noting down, which may be useful later on. This I said is a time evolution operator, but you can also associate operators for spatial displacement. I'll give you an example. So you could have a spatial, learn to use this better. So spatial displacement can be some, let's say I'm moving in x, e over minus I, x cross. That's a displacement operator. You can also have, for example, rotation. So if I have to do rotation, let's say some added phi, e over minus I phi, later or h cross. Of course, these are just telling you the generality of exponential operators. We are not going to use spatial displacement or rotational displacement. We're going to focus only on the time evolution operator. Because your spectroscopists, ultrafast guys, we live in time domain. So that's the most important thing, is the time evolution. Cool. So what is the utility of time evolution operator? As noted earlier, if I know my wave function, let's say at time t0, I should be able to predict what is my wave function at a later time t simply by using time evolution operator. That is at the heart of this endeavor. Okay. So in the simplest case, simplest scenario, let's say your Hamiltonian is time independent. So we'll take first scenario, time independent Hamiltonian. Then your time dependent Schrodinger equation, of course, will be d over dt psi of t plus I h, which is now independent of time, psi of t 0. Now we define, as we defined earlier, we still don't know, I haven't shown what u should be. Let's say I take my exponential operator to be minus, e power minus I h t over h cross. I'm defining this as my exponential operator, so I should be able to expand out if needed by expanding out the exponential function. So forth, right? Now I can also write inverse. You can verify if the t satisfies the two properties of exponential operators, and it does. So what we will do is we take our Schrodinger equation and we multiply by the inverse of the exponential operator. Then what we will get is d over dt e power r h t h cross t 0 integrating from t to t naught. You can see in this case sine of rt power minus I h t minus t naught over h cross sine r t 0. Okay. I'm not solving everything. I can give you notes. This is so basically if I compare this and this, kind of see u of t naught simply e power plus I h minus t naught h cross. Okay, that is for a time independent Hamiltonian. So that's my time evolution. So if I know that a solution to a function of my time independent Hamiltonian, then I can predict what will be my wave function at later time simply by operating this u. By the way, please let me know if my fonts are too small. Are they too small? So maybe I'll expand it. Okay, clear? Clear? In fact, you can expand it out and because you know the solutions for this Hamiltonian, you can see this is simply equal to power I n minus t naught h cross. This is all good, but for us, we don't have time independent Hamiltonians. We are dealing with time dependent Hamiltonians, particularly in spectroscopy. So we have to kind of figure out a way to estimate my time evolution operator in the case where my Hamiltonian is time dependent. Okay. So because your Hamiltonian is time dependent, we have to write out some kind of equation. What we are looking for is some kind of equation of motion for your time evolution operator. So at the end, if you think about it in spectroscopy, what we are doing, we are coming with optical pulses at different times, and you want to see what will happen to my state at a later time, right? So my time evolution operator is a very critical aspect in the formalism. I need to figure that out. That's a very important thing. Now, one note here is we are working in the Schrodinger picture, which you will see is kind of not an ideal thing to do for spectroscopy. We will soon move into interaction picture, but rather, in any way, we want to get the concepts right. We will never be doing anything in Schrodinger picture. Anyway. Okay, so what we want is equation of motion of my time evolution operator for a Hamiltonian which is time dependent. Now here I'm going to make a consideration. If I take my time evolution operator which links my wave function at time t, and t plus delta t, under the limit delta t tends to 0, can anybody tell me what this should be? So I'm sorry, I made a mistake. Mistake in the sense, things are small. Let me expand this out even more. So I'm saying, if I take my time evolution operator, which links my wave function at a time t plus delta t with the wave function at t, but under the limit delta t tends to 0, what this should be. 1. Can anybody else tell why? Because you have not evolved. You're basically in the same state. So it should be 1. Because the state has not moved anywhere. Okay? So that's a very important thing. But let's say for small delta t, it is reasonable to say u of t varies linearly. That's my consideration. That's how I'm going to work, which is reasonable. Okay, when I'm in the same place, okay, fine. If it's small, I can approximate to a linear this thing. So I can write u of t. I'm dropping the operators for now. Will be some u of t minus I sigma t some slope delta t. It's a linear relationship. Note this guy. Why do we have the complex argument? Any idea? I'll not go into details, but I'm going to give you an answer. You can mull over it. If you don't do it, if you don't have a complex argument, then P of the probability density will oscillate forever. But that's not physical. It has to decay for some point. So you need to have that imaginary complex argument in there, so that the probability density is decaying. Okay, so that's my consideration. I'm able to write it out. So I can now write out. Of course, I can now from combining these two, we can kind of see. Minus I, technically sigma is an operator. Fair enough? If I write my sigma, actually it's related to my Hamiltonian. Then I should write this as cross t. So I have an equation of motion. Right? I have an equation of motion there. Cool. So I should be able to solve this and get a form for my time evolution operator in the case I have time dependent Hamiltonian. Okay, so let's try this. Let's try to integrate this. I'm going to rewrite this. I remember this already. So I'm going to see if I take cross d over dt naught h d naught. You also know that if I multiply by psi of t naught on both sides, you'll get time dependent equation. But if integrate this out, you will get u t naught basically exponential minus I h cross integral 0 to t, so some t prime, t prime. Fairly simple integral there. Looks very nice and easy to solve, but we'll take another look. If this is really true, one may be tempted to expand that exponential. We know we can expand that exponential. And if I just expand this exponential, you will see this will be so on and so forth. Seems a pretty reasonably good expansion to solve out, but you will see that this is not a general solution, and it will only work if I have this condition. Relationship. Otherwise, I will not be able to write it out like this. Okay, which is a very specific condition, and particularly in ultrafast spectroscopy, mostly it's not valid. Okay. You can later on go and kind of write this out yourself and kind of check if this is true. So this kind of direct solution, this exponential form, is not leading us to a general solution. It may be valid in specific cases where this condition is satisfied. So if I go back here, go back to my equation, I'm going to take this equation back here, and if I want to directly integrate this again, then you will see my u d naught will be d over h cross integral d naught d tau h of tau u of tau d naught. You can verify this as well. Now, if you look at this solution, let's look at this solution, which is a solution of that equation. Let's focus on this solution. Does anybody find a problem or an issue with this solution? Just mathematically speaking, just look at that equation there and say, okay, is this a practical solution? To find the form of u of t naught, you already need to know its form. You see, this is inside the integral, right? So u of t naught is a function of itself, which is not a practical thing. It's kind of not useful, right? So what we can do now is make an iterative expansion, okay, of this. Let's see if we can find, at least in an approximate way, some approximate solution. So we're going to make an iterative expansion of that. Get a bit cumbersome, bear with me, and it will be beautiful. Just 1 minus I over h cross integral t naught t tau tau. I'm going to expand out again u of tau inside, so it will be 1 minus I over h cross integral t naught to tau now, tau h of some tau prime u of tau prime tau naught. Again, didn't help us in any way, because again you're left with u. Let's expand it again once more. So if I keep expanding this out, tau of tau plus h cross square integral t naught t tau t naught tau tau prime h of tau prime u of tau prime t naught. Again, I'm left with u of tau prime t naught. And so I can keep on expanding this out to multiple orders. I can expand to third order. That's what I'm going to do now because it's the most convenient way of representing this. I have 1 plus I h cross t naught t tau of tau. You might be wondering, why am I doing this? Bear with me. T tau naught tau prime tau prime cube t tau t naught tau prime integral t naught prime t tau prime tau prime prime u. Not really solving anything, but an important aspect in solving this equation, a very important aspect, is there has to be what we call as time ordering. Meaning t naught always be less than or equal to prime tau prime tau to t. Okay, that's otherwise this is not a general solution anymore. Remember, there are these products of Hamiltonians, and if I don't impose this, then it would go all over the place. So what is physically this mathematically complex looking, seemingly impractical expansion tells? It tells us that, let's say I'm going from some initial state to some final state. I could go from here to here, let's say in some time tau. So this is my first stop in this case. That's my first stop. I could also go to my final state through sort of an intermediate state. I could go to some k and go here. Here, now this will be tau prime, tau. Or I could go, I can expand this out. I could have another state m, another state n, no, this, like this. So all of this is my term 1, this is my term 2, this is my term 3 in this iterative expansion. So basically this expression of u sort of tells you, describes you all possible pathways between my initial and final states. Okay? All possible pathways. Now at this point in time, it may not make any sense. It will make an absolute sense once I move to interaction picture and write everything down in density matrix, which I will do in some time. But basically, I'm able to write the time evolution operator, expand it out, and can describe by all possible pathways between initial and final states. And remember, these pathways may constructively or destructively interfere. Okay, that's a very important thing. So, depending on my interaction, I will have a few excitation pathways which leads to my final state. Some may not lead to that final state. Okay, this you will see is at the core of nonlinear spectroscopy. By controlling the so-called phase matching conditions in your experiment, you can have or you can invoke specific excitation pathways. Okay, by specifically constructively interfering some pathways. Okay, so this kind of expression, just for the sake of completeness, I'm now going to write down the final expression for this for this u of t naught in the most general sense. It is 1 plus summation equal to 1 to infinity. Sometimes this is referred to as an operator associated with it. This is referred to as the Dyson partner operator. The time ordering is critical. I'll give a little homework assignment later tonight or tomorrow, which you can kind on this Dyson operators to Dyson expansion. We won't be using specifically this form, but this kind of form kind of comes up again. We can take a short break now. And when we come back, I'm going to rewrite this stuff in the so-called interaction picture. Okay. So something that I have not done here, which we will do in the next class, hopefully, is I have not introduced an appropriate Hamiltonian for spectroscopy yet. So there is a time-dependent part of the Hamiltonian. Right? If I have a time dependence of the Hamiltonian, I know how to kind of figure out my time evolution. Cool. But in spectroscopy, specifically in light matter interaction, how should that time-dependent part look like? Okay, that's a very important part of this. The next class I'm going to introduce as a time-dependent potential. Your Hamiltonian, this is generic spectroscopy. Generic spectroscopy, your time-dependent Hamiltonian as a time-independent part plus a time-dependent potential. Okay, and this potential is exclusively coming from light matter interaction. Later on, we will show this is given by minus mu dot E under dipole approximation. There are several approximations that go into it, but that will be the goal. And we will be using that extensively. Once we have that, and of course, write down this U time evolution operator in the so-called interaction picture, where we will develop concept of density matrix, then we have all the tools to really get into nonlinear spectroscopy. Any questions so far? You can kind of tell me if there are parts where I'm kind of rushing through, parts I'm kind of repeating boring stuff. Kind of tell me. Okay, we can take a little break now.